Have you ever wondered how humanity managed to send things into space and keep them there circling around our planet? The birth of orbit engineering didn't happen overnight. It began with the understanding of some fundamental principles of physics, principles that were introduced by none other than Sir Isaac Newton. Newton's laws of motion and universal gravitation are the cornerstones of orbit engineering. These laws explain why an apple falls to the ground and why the moon doesn't just fly off into space. They tell us that an object in motion stays in motion and that every action has an equal and opposite reaction. The moon, you see, is in a constant state of falling towards Earth, but it also moves forward fast enough to miss it. That's an orbit. Newton's laws helped us understand this fascinating dance between gravity and inertia, and it's these very principles that set the stage for the space age. The dawn of the space age introduced us to the practical application of these principles. Our journey begins in the year 1957, when a metal sphere, no larger than a beach ball, was hurled into the sky. This was Sputnik 1, the pioneer of artificial satellites launched by the Soviet Union. It was a game-changer, the opening salvo of the space age, and the birth of orbit engineering. Sputnik 1, with its simple design and beeping radio signals, was a marvel of engineering. It was the first man-made object to orbit our planet, a feat that seemed almost fantastical at the time. But it was real, and it marked a turning point in our relationship with the cosmos. Space was no longer a distant, unattainable frontier. It was now a destination. With the launch of Sputnik 1, the world watched in awe and trepidation as the once impossible became possible. The race to space was on, and nations across the globe threw their hats into the ring. From that moment forward, space exploration took off at a breakneck pace, and the complexity of orbits grew exponentially. The advent of manned space missions brought with it new challenges that pushed the boundaries of orbit engineering. The simple circular orbit of Sputnik 1 was a far cry from the intricate and diverse orbits we see today. Now we have geostationary orbits, polar orbits, and even highly eccentric orbits, each with their own unique set of engineering challenges. Space exploration also brought about the need for more sophisticated satellites. These technological marvels serve a multitude of purposes, from weather forecasting and global communications to scientific research and military surveillance. The orbits of these satellites are meticulously designed and engineered to ensure their functionality and longevity. The dawn of the space age was a time of rapid progress and innovation. It was a time when the impossible became possible, and the unattainable became attainable. It was a time that forever changed our understanding of the cosmos and our place within it. The space age brought with it a new era of exploration and a host of new challenges. Space exploration is not as simple as launching a rocket and hoping for the best. This statement rings true, especially when we delve into the intricate world of orbit engineering. The challenges engineers face when planning and executing space missions are colossal, with precision and accuracy being paramount. An orbit isn't just a path a spacecraft follows. It's a delicate balance, a dance if you will, choreographed by the laws of physics. This dance is affected by a myriad of variables, each with its own unique impact. Let's consider gravity, our first variable. While it helps us stay grounded on Earth, it's a whole different ballgame in space. The gravitational pull of celestial bodies influences the trajectory of spacecraft, requiring engineers to calculate orbits with pinpoint accuracy. Next, we have atmospheric drag. As a spacecraft re-enters the Earth's atmosphere, it experiences drag. This force slows down the spacecraft, affecting its orbit and requiring adjustments to ensure a safe return. Then, there's solar radiation. The sun, while being the source of life, can also be a source of problems for spacecraft. Solar radiation can heat up spacecraft, affecting their electronics and potentially knocking them off course. These variables, among others, pose significant challenges to engineers. However, they also play an essential role in mission control, the nerve center of any space mission. Here, teams of engineers monitor and adjust orbits in real time, taking into account all these variables. Mission control is an orchestra of sorts, where each engineer plays their part in harmony, ensuring the spacecraft maintains its intended orbit and completes its mission. It's a complex process, requiring a deep understanding of physics and engineering, and the ability to make quick, informed decisions. These challenges are not just obstacles to overcome, they are opportunities for innovation and learning, pushing the boundaries of what we understand about physics and engineering. They have led to leaps in technology and have expanded our understanding of the universe. These challenges have pushed our understanding of physics and engineering to new heights. They have shown us that the sky is not the limit, but rather the beginning of an endless journey of discovery. Modern orbit engineering has led to some truly remarkable achievements. In the grand theater of the cosmos, we've erected stages that defy gravity and distance, creating spectacles that would have been unimaginable mere decades ago. Take the International Space Station, for instance, a marvel of engineering that orbits Earth at an altitude of roughly 250 miles. It travels at a staggering speed of about 17,500 miles per hour. This feat of orbit engineering allows astronauts from around the globe to live and work in space, conducting crucial experiments and research that deepen our understanding of life beyond our planet. Then there are the Global Positioning System satellites, a constellation of 24 main satellites orbiting the Earth at an altitude of over 12,000 miles. These satellites, with their highly precise orbits, provide the backbone for the GPS services we take for granted today. Whether you're navigating city streets or exploring remote wilderness, it's the intricate dance of these satellites that guides you. And let's not forget the various Mars rovers, our robotic emissaries exploring the Red Planet. These rovers didn't just get to Mars by chance. They relied on complex orbits and extraordinarily precise calculations to make the journey of millions of miles. The rovers' journeys are a testament to the incredible advancements in orbit engineering, enabling us to reach further into the cosmos than ever before. Each of these accomplishments is a symphony of science, engineering, and mathematics. They represent the culmination of countless hours of work, sophisticated calculations, and the unyielding determination of engineers around the world. These modern marvels of orbit engineering are not just machines or systems. They are the physical embodiment of human curiosity, ambition, and ingenuity. These modern marvels are a testament to the ingenuity and skill of our engineers. They remind us of our incredible potential when we reach for the stars, literally. And they inspire us to continue pushing the boundaries of what's possible, to keep exploring and to keep engineering the future. As we look to the future, the possibilities for orbit engineering are almost limitless. Imagine a future where we're not just sending rovers to Mars, but people. This is not just a dream anymore. It's a reality that orbit engineers are diligently working towards. The journey to Mars is a complex one, with numerous engineering challenges to overcome. For instance, a manned spacecraft would need to be equipped with advanced life support systems to ensure the safety of astronauts during the long journey. Furthermore, engineers would need to design a way for the spacecraft to land and take off from Mars's surface, a task made difficult by the planet's thin atmosphere and dusty terrain. Despite these challenges, the prospect of sending humans to Mars isn't just a testament to our ambition, it also represents a new frontier for orbit engineering. But our journey doesn't stop at Mars. With the rise of space tourism, orbit engineering is set to take a more commercialized route. Companies are already planning to offer commercial flights to the edge of space, giving people a chance to experience the sensation of weightlessness and the beauty of our planet, from a perspective few have seen. Yet, space tourism also presents its own set of engineering challenges. Engineers will have to construct spacecraft that are not only safe and reliable, but also comfortable for the average person. They will also need to develop reusable spacecraft to make space tourism economically feasible. The future of orbit engineering also holds potential for even more groundbreaking innovations. We might see the construction of space elevators, reducing the cost of space travel dramatically. Or perhaps the establishment of permanent settlements on other planets or moons, pushing the boundaries of what humanity can achieve. As we continue to venture into the unknown, we are constantly redefining what's possible in orbit engineering. Every challenge we overcome, every boundary we push, brings us one step closer to a future where space is no longer the final frontier, but a new beginning. As we continue to push the limits of our knowledge and skills, who knows what the future of orbit engineering holds? So to recap, the engineering of orbits is a complex and fascinating field. From the birth of orbit engineering, where it was all about understanding the fundamental principles of orbits, to the dawn of the space age, where the dream of exploring the cosmos became a reality. We've discussed the immense challenges posed by orbit engineering, from the technical to the environmental, and how they have been navigated with a combination of ingenuity and perseverance. Then, we explored the modern marvels of orbit engineering, showcasing how these advancements have revolutionized our capabilities in space exploration and satellite technology. We also looked ahead to the potential future of the field, where we can expect even more impressive feats of engineering as we push the boundaries of what's possible. As we continue to explore the cosmos, the engineering of orbits will undoubtedly continue to play a crucial role in our journey.